Alright, so today we talk about the random samples. So in this video, we talk about the way to collect the data from a finite population, from an experiment, from an ongoing process. So let's get started. Back to the core weighting service. We want to use statistical inference to draw conclusions about the population of all customers based on a sample. To make valid inferences, we need to know the right approach to taking a sample. A special type of samples that is critical to statistical inference is a random sample. In a random sample, every member of the population has an equal chance of being included in the sample. Members of the sample are selected independently of each other so that no one's chance of being selected is affected by the other members of the sample. So why is this so important to take a random sample? Random samples are more likely to be representative of the population. They allow us to quantify how well they represent the population. So a random sample provides precisely the kind of information we need to draw statistical inferences. Let's see how we take a random sample from the survey. We determine we want to sample 400 customers from the population of interest, the 100,000 current customers. To do this, we obtain a spreadsheet list of all the customers and use this statistical software to take a random sample of 400 customers. A unique feature of this example is that there is a finite population, a fixed collection of customers that we can list and draw our random sample from. In many business settings, we don't have a fixed population from which to draw a random sample. Instead, our data may be from an experiment or an ongoing manufacturing process. Fortunately, we can often treat these kinds of data as if they are random samples, allowing us to draw statistical inferences. Okay, so let's see how. Okay, here the we use Minitab to collect the random sample from a finite population. You can see here the step by step to collect the random sample. Okay, so now we have 400 customers from the finite population of 100,000 customers. In an experiment, we systematically test different conditions to measure how they affect some variable of interest. For example, the paint engineers could apply a new adhesive formula to one set of plastic sheets and the current formula to another set. They could then subject to the plastic sheets to room conditions and then measure the adhesive strength of these sheets to do statistical inference about the difference between the two formulas. The engineers must run the experiment properly. So how do they do this? They should conduct the experiment under consistent conditions. For example, they should follow a uniform procedure for painting and measuring each sheet, and they should use a thermostat to control the temperature of the testing environment. But the engineers can't control everything. Differences that are unknown to them are sure to exist in the experimental setting. For example, plastic sheets may differ, humidity may rise or fall while the sheets are being coated. Conditions may vary depending on where a sheet is placed within the chamber that simulates extreme weather conditions. The engineers don't want to conclude that these of other differences are due to differences in the two formulas. So how can they avoid this? They can randomize certain aspects of the experiment. For example, they can randomize a set assignment of the sheets to the two formulas, the order in which they paint and measure the bar, the sheets, and even the position of the sheets within the test chamber. Randomization has two benefits that allow the engineers to make valid statistical inferences based on the data from the experiment. It reduces the chance that differences in materials or conditions strongly favor one formula over the other, and it allows us to estimate the variation inherent in the experimental conditions so we can quantify the risk associated with the inferences. In other words, randomization lets us treat the data for the two formulas as random samples. So how about the data sample from an ongoing process? For example, consider the process that manufactures mobile phones. There is no fixed population from which to sample. Throughout the day, we sample phones from the line and measure the weight of the phones. The phones are supposed to have a 140 grams. So how can we draw statistical inferences about how well the process is doing? For us to make reliable statistical inferences from the samples we take, we must assume that each sample is representative of the process in the same way that a random sample is representative of a population. This requires the process that makes the phones is stable. So what is a stable process? A stable process is one in which the inputs and conditions are consistent over time. Any variation must occur in essentially random order. So if, for example, the process is sensitive to changes in temperature, it will not remain stable if the temperature rises steadily throughout the day. To keep the process stable, we could regulate the temperature or alter the process so that it was no longer sensitive to temperature variation. And a stable process is said to be in control. We, can, we cannot take for granted that a process is stable, and a process that is stable now will not necessarily remain stable indefinitely. In next lesson, the contrast, you learn about statistical methods for monitoring a process to see whether it's stable and to detect when it goes out of control. For now, it's enough to know that if we are sampling from a stable process, we can make statistical inferences from short-term data that apply to the process as long as it remains stable. We can treat the samples as a random sample that represents the process over a long time period. Let's review. Statistical inference is an effective way to draw conclusions about an entire population based on data from a subset. However, we must be careful how we collect data. We should take a random sample so that the data will be representative of the population. A random sample allows us to quantify how well the sample represents the population. We can also treat data from a randomized experiment or a stable process as a random sample for purposes of statistical inference. Thank you for listening. In the next lesson, we talk about the sampling distribution.